engineers look at the Google interview process and assume it tests their ability to memorize obscure coding trivia or solve esoteric puzzles. The process functions as a highly standardized evaluation framework designed to map candidate responses against specific architectural markers and algorithmic scaling patterns. To understand how you are graded, you have to look at the engineering hierarchy. Google categorizes candidates into specific L bands, primarily L3, L4, and L5, and each level dictates a strict evaluation threshold you must cross. If you are entering as an L3, which is the new grad or entry-level tier, the rubric is heavily weighted toward data structures and algorithms. The expectation is almost entirely about your ability to optimize code and solve complex logic problems. Moving up to L4 and L5 changes the equation. Here, component system design and large-scale architecture enter the matrix. The expectation shifts from simply writing code to navigating deep ambiguity and constructing global infrastructure. Looking at this rubric for the coding rounds, the panel prioritizes your ability to present and defend multiple solution approaches over simple code compilation. Success at Google requires reverse engineering this exact rubric, moving away from brute force problem solving and toward a focus on architectural trade-off analysis. When we look at the specific data architecture tested most frequently at Google, one category dominates the technical loop: hierarchical and networked data, trees and graphs. There is a precise reason for this focus. Google's core products, from the search index to Google Maps, rely on graph traversal systems to function at scale. A classic target problem requires navigating a 2D matrix to map connected components. An underprepared candidate will execute a brute force recursive check, originating a new path from every cell. Because this repeatedly visits the same pathways, the time complexity spirals into O of n squared. In a production environment, code structured this way results in significant performance bottlenecks. In an interview, it serves as a strong negative signal regarding your ability to handle scale. Applying a brute force recursion to a matrix proves to the interviewer that you cannot conceptually scale logic to Google's data volumes. To solve this optimally, you must stop seeing a grid and start seeing an adjacency graph. Once you map the grid to a graph, you can apply the optimal algorithmic framework, a breadth-first search or a depth-first search. Implementing a visited state tracker using a hash set or an array is mandatory to keep the traversal efficient. Tracking visited states eliminates the infinite loops and redundant recursive calls that crash the naive approach. The time complexity drops from an exponential state down to a linear O of v plus e, meaning you process each vertex and edge exactly once. The interviewer will then press you on a secondary constraint, space complexity. An optimal solution must maintain a minimal memory footprint. You need to compare the specific trade-offs. In a breadth-first search, your space complexity is defined by the maximum width of the graph. In a depth-first search, you are bound by the call stack limit dictated by the graph's maximum depth. Mastering this architectural transition provides the evidence of technical maturity required to advance through the technical loop. You also have to execute this logic under severe environmental constraints. Google often tests candidates using a plain text editor or a blank Google Doc. There is no syntax highlighting, no autocomplete, and no compiler to catch a missed semicolon or a misspelled variable. This setup enforces strict professional code hygiene. You are expected to use precise, meaningful variable names and adhere flawlessly to a single casing convention, such as camel case or snake case. A highly prepared candidate will also write inline comments defining the precise time and space complexity before the interviewer even asks for it. You must also handle edge cases up front, checking for empty arrays, null pointers, and out-of-bounds matrices before writing the core logic. Your code must be both mathematically flawless and perfectly readable to another human being. For L4 and L5 candidates, algorithmic mastery is only half the battle. You must also pass the system design round. These scalable design topics show the shift toward infrastructure problems, requiring knowledge of sharding, caching, and network protocols. Consider the classic prompt: design Google Drive. This requires managing massive concurrent metadata updates and high-throughput block storage across a global distributed network. The most common failure point in this round is jumping into architecture diagrams before you have actually defined the constraints of the system. Your first step is to interrogate the interviewer. Define the daily active users, the specific read-to-write ratios, and the exact media storage constraints. Once the scope is locked, the round becomes an exercise in explicit trade-off framing. Success here relies on providing mathematical justification for every architectural compromise. For example, choosing a NoSQL database for high write throughput means you must explicitly defend the compromise regarding strict data consistency. System design is about mathematically defending the least bad trade-offs at planetary scale. The final hurdle of the on-site loop is the Googleyness and leadership round. It is a mistake to treat Googleyness as a vague culture fit test. It is a structured evaluation of your intellectual humility, your capacity to navigate deep ambiguity, and your bias for action. Every behavioral question requires the STAR method, defining the situation, task, action, and result. You must focus on the result. Subjective outcomes are ignored. Your answers must feature hard, quantifiable metrics proving your impact. This behavioral rigor integrates with your performance in the technical rounds to form your complete engineering profile. To crack Google, you must demonstrate 3 things. You can scale algorithms flawlessly, architect distributed systems logically, and scale your team's impact behaviorally.